Let's take a look at Chapter 14, Section 14.1. In 14.1, we're looking at organizing and visualizing data. We want to understand the difference between the sample and the population. We want to organize data in frequency tables. We want to use a variety of methods to represent visual data. And we want to use stem and leaf displays to compare data. Populations and samples. Statistics is an area of mathematics in which we are interested in gathering, organizing, analyzing, and making predictions from numerical information called data. The set of all items under consideration is called the population. Often only a sample or subset of the population is considered. We will describe a sample as biased if it does not accurately reflect the population as a whole with regard to the data that we are gathering. Bias could occur because of the way in which we decide how to choose the people to participate in the survey. This is called selection bias. Another issue that can affect the reliability of a survey is the way we ask the questions, in which is called leading question bias. Frequency tables. Definition. We refer to a collection of numerical information as data or a distribution. A set of data listed with their frequencies is called a frequency distribution. We show the percent of the time that each item occurs in a frequency distribution using a relative frequency distribution. We often present a frequency distribution as a frequency table where we list the values in one column and the frequencies of the values in the other column, in another column. Example of a frequency table. 25 viewers evaluated the latest episode of CSI. The possible evaluations are E for excellent, A for above average, D for average, B for below average, and P for poor. So we have 5 ratings: excellent, above average, average, below average, and poor. After the show, the 25 evaluations were as follows: AVV, BPE, AEV, VAE, PBVV, AAA, EBVA, BV. Construct a frequency table and a relative frequency table for this list of evaluations. Solution. We organize the data in the frequency table shown below, where we have one column of the evaluation response and one column of the corresponding frequencies. So each row reads E for 4, A 7, V 8, B 4, and P 2, for a total of 25 responses. This is a frequency table. We construct a relative frequency distribution for these data by dividing each frequency in the table by 25. For example, the relative frequency of E is 4 divided by 25, which equals 0.16. A has a relative frequency of 7 divided by 25. V has a relative frequency of 8 divided by 25. B has a relative frequency of 4 divided by 25. And P has a relative frequency of 2 divided by 25. If you sum the total of the relative frequencies, your total will sum to 1. Another example. Suppose 40 healthcare workers take an AIDS awareness test and earn the following scores. So we have 1, 2, 3, 4 rows of 10 different scores, giving us 40 scores for 40 healthcare workers. Construct a frequency table and a relative frequency table for these data. The solution here is to make a bin, to make an interval of numbers. Because there are so many different scores in the list, the data is grouped in ranges. So 50 to 54, 55 to 59, 60 to 64, 65 to 69, 70 to 74, 75 to 79, 80 to 84, 85 to 89. Those are the ranges, the range of scores on the AIDS awareness test. Notice we don't have a range for entries below 50, and we don't have ranges for above 89. Each frequency then is listed at 2 for 50 to 54, 3 for 55 to 59, 5 for 60 to 64, 6 for 65 to 69, 4 for 70 to 74, 9 for 75 to 79, 7 for 80 to 84, 4 for 85 to 89, giving us a total number of frequencies of 40, which is the number of scores we originally had. We divide each count in the frequency column by 40. For example, in the row labeled 55 to 59, we divide 3 by 40 to get 0.075 in the third column. So you'll have an X column, you'll have a data column, the actual data that we saw in the example or that we collected from our sample, and we'll have a frequency column. Third, we'll have the relative frequency column, where we've taken each frequency and divided individually by 40. So 2 divided by 40, 3 divided by 40, 5 divided by 40, 6 divided by 40, 4 divided by 40, 9 divided by 40, 7 divided by 40, and 4 divided by 40. If we sum the relative frequency column, we should sum to 1. Representing data visually. A bar graph is one way to visualize a frequency distribution. In drawing a bar graph, we specify the classes on the horizontal axis and the frequencies on the vertical axis. If we are graphing a relative frequency distribution, then the heights of the bars correspond to the size of the relative frequencies. Graphing the relative frequencies rather than actual values in data sets allows us to compare the distribution. Example, draw a bar graph for the frequency distribution of visitors' responses to an episode of CSI. So here we have our frequency table of EAVBP with frequencies 4, 7, 8, or 2. And we can put the EAVBP on the horizontal axis and the frequencies on the vertical axis. Notice there's a space between each bar. The E goes up to the height 4, A goes to the height 7, V goes to the height 8, B goes to the height 4, and P goes to the height 2. The same numbers on the frequency table. Draw a bar graph of relative frequency distribution of viewer responses to an episode of CSI. Now this is 4 divided by 25, 7 divided by 25, 8 divided by 25, 4 divided by 25, and 2 divided by 25, our relative frequencies. Notice the image, the bars are exactly the same. What's different is the labeling on the horizontal axis. On the vertical axis. The bar graph for the relative frequency is shown below. So still on the horizontal, we have EAVBP, the viewer's ratings, but now on the vertical axis, we have 0, 5, 10, 15 in percentages. So dividing 4 by 25, for example, was E. So now E goes up to the 16%. And B was 4 divided by 25, also goes up to the 16%. Representing data visually. A variable quantity that cannot take on arbitrary values is called discrete. Other quantities called continuous variables can take on arbitrary values. The number of children in a family is an example of a discrete variable. Weight is an example of a continuous variable. We use a special type of bar graph called a histogram to graph a frequency distribution when we are dealing with a continuous variable quantity or a large variable quantity that is discrete, but has a very large number of different possible values. Representing data visually. Example, a clinic has the following data regarding the weight lost by its clients over the past 6 months. Draw a histogram for the relative frequency distribution for these data. Pounds lost is our first column, the frequency in the second column. Now we have a range of values, 0 to 10, 10 plus to 20, 20 plus to 30, 30 plus to 40, 40 plus to 50. So if you lost 10.01 pounds, you're in the second row. And our frequencies are listed at 14 people lost between 0 and 10 pounds, 23 people lost 10 plus to 20 pounds, 17 people lost 20 plus to 30 pounds, 8 people lost 30 plus to 40 pounds, and 3 people lost 40 plus to 50. Now we also construct a relative frequency column. If we add up the individual frequencies, we have a total of 65. If we divide 14 by 65, we get 0.215. 23 divided by 65 gives us 0.354. 17 divided by 65 is 0.262. 8 divided by 65 is 0.123. 3 divided by 65 is 0.046. If we sum the relative frequency column, then we will sum to 1. Now, representing this data visually, we draw a histogram exactly like a bar graph, except we do not allow spaces between the bars. So between 0 to 10, we have 22.5%, 21.5%. From 10 to 20 pounds, we go up a little above the 35%, 35.4, right? So in a bar graph, the bars do not touch. In a histogram, the bars do touch because there are intervals of data. In this example, the bar graph shows the number of Atlantic hurricanes over a period of years. Answer the following questions. Answer the questions on the slide that follows. Okay, so we've got a frequency on the vertical axis. We've got discrete numbers on the horizontal axis, which represents the number of hurricanes per year. You don't have 4.5 hurricanes ever. You have 4 or you have 5. And what else do we have? It's a bar graph, right? The bars are not touching. Another indication we have discrete data. What was the smallest number of hurricanes in a year during this period? And what was the largest? What was the smallest number of hurricanes? Well, in year 15, 16, 17, we didn't have any hurricanes, right? And it says the smallest number of hurricanes in any year during this time period was 4. The largest was 19. Maybe I'm missing something. Oh, number of hurricanes is on the bottom. Okay, got it. So each year, it's not that this is year 4, this is the number of hurricanes, right? So there were 4 hurricanes reported once. There were 5 hurricanes reported once, 1 year, right? In 1, 2, 3, 4, 5, 6 individual years, 6 hurricanes were reported. In 10 individual years, 11 hurricanes were reported. Okay, got it. So now, what was the smallest number of hurricanes in a year during this period? Number of hurricanes on the horizontal axis. 4 is our smallest possible number of hurricanes. And what was the largest? 19. Luckily, we have the solution typed out. The smallest number of hurricanes in any year during this time period was 4. The largest number was 19. What number of hurricanes per year occurred most frequently? So that was the 11 we pointed out, right? Because that one goes all the way up to the 10. No other amount of hurricanes goes up to the 10. And so for the number of hurricanes per year, that would be 11. The answer they provided is we look for the tallest bar, which appears over the number 11. Therefore, 11 hurricanes occurred in 10 different years. And C reads, how many years were the hurricanes counted? And the solution is to count the number of frequencies and add your frequencies together. So we have 1 plus 1 plus 6 plus 6 plus 9 plus 4 plus 6 plus 10 plus 5 plus 5 plus 3 plus 1 plus 1. It looks as though we have 58 years being recorded. And question D reads, in what percentage of those years were there more than 10 hurricanes? So for more than 10 hurricanes, we don't want to count those from 10. So we have 10 hurricanes that reported at 11, 10 years that reported 11, right? Then we have 5, 5, 3, 1, 1. So the number of years, right? We count the number of years in which there were more than 10 hurricanes and add the height of the bars above these values, 10 plus 5 plus 5 plus 3 plus 1 plus 1, which equals 25. There are 58 years of data, so 25 divided by 58 gives us 0.431. So what percentage of the years were there more than 10 hurricanes? 43.1%. Now let's look at the stem and leaf display. Here's our example. The following are the number of home runs hit by the home run champions in the National League for the years 1975 to 1989 and for 1993 to 2007. So from 1975 to 1989, we have 2, 4, 6, 8, 10, 12, 14, 15 different scores, different amounts of home run hits by the home run champions in the National League for that year. And we have 15 years listed, 493 to 2007. Also with number of home runs hit by the home run champions in the National League. Compare these home run records using a stem and leaf display. And already I see like 70s and 50s down here, 60. There's nothing like that. There's a 52 in this first round. Compare these home run records using a stem and leaf plot. So what we do in constructing a stem and leaf display, we view each number as having two parts. The left digit is considered the stem and the right digit the leaf. For example, 38 has a stem of 3 and a leaf of 8. And by convention, you order going downward. You also order going from left to right or center outward. So you start at your stem and you grow outward. So organizing the data, we look through our list. The lowest stem we have is a 3, so we start with 3. We also have stems of 4 and a stem of 5. Then when we're going to fill in our chart, we take our 3s, all of our 3s, then we order them. So here's our 31. So first we write a 1 in the chart, and then we look for what's next, right? 36. So here we have a 1, a 6, 3 7s, 2 8s. That's 31, 36, 37, 37. So here we've ordered our list. And what you want to note is when you make this stem leaf plot, you're also forming columns in your leaves, and you do represent duplications, right? So it on the left side, we can see the years from 1975 to 1989. And on the right, we see the years from 1993 to 2007. And in that stem, we needed a 4, 5, 6, 7. So the stems are slightly different. We can compare these data by placing these two displays side by side as shown below. Some call this display a back-to-back stem and leaf display. So what they did was they took the 1975 to 1989 and they grew the numbers from center outward. So this time, instead of the numbers increasing from left to right, they're going to increase from right to left, because you're imagining a tree, you're imagining a leaf, and how a leaf grows, right? A leaf grows from the stem outward. And so from the stem outward is how you grow your numbers, right? Okay. It is clear that the home run champions hit significantly more home runs from 1993 to 2007 than from 1975 to 1989.